Hi everyone. Today I'll talk about the dawn time and twilight time in quantum tunneling based on my recent work on arXiv. The main goal of this project is to explore the time evolution structure of metastable decay, in particular when the exponential decay begins and ends. The metastable decay is central to many areas in physics, for example, in force vacuum decay in QFT and the cosmological phase transition in early universe. The standard pictures assumes an exponential decay characterized by a decay rate gamma. However, it raises two basic questions. When does the exponential decay start and when does it end? The standard method to calculate the decay rate was the so-called famous Euclidean bounce method developed by Coleman and Callan in 1970s using the wake rotation and analytical continuation of the potential, assuming a time-independent background. However, in realistic situation, this assumption is not always valid. For example, for early universe, electroweak phase transitions, the effective potential evolved and the bubble nucleation occurs in a time-dependent environment. And this motivates an alternative real-time direct approach to calculate the exponential decay rate developed by Harvard's Schwartz group at 2016. They use numerical simulation to solve the one-dimensional coordinate equation and found an exponential decay regime with an beginning time and ending time. And directly using the path integral, they found the same decaying rate as the Coleman and Callan's methods suggest. However, in their work, they didn't give the analytical expression for the beginning time and ending time of the exponential decay regime, and that's what we solved in our work. So first, we come back to some basic concept of decay and kernel. Here we assume a general potential which we'll study later. And this E represents the energy of the initial particle or the initial wave packet trapped in the left region or the well region of the potential. To find the decay rate, to find an exponential decay regime, an intuitive idea is to obtain the probability of finding a particle or finding the wave packet at the left region, at the well region at time t. And if we find an exponential function form in this probability pt, then we found the exponential decay that we want. To find that probability, a very direct method is to use the kernel in path integral method of quantum mechanics, of which expression is showed below this potential plot. So here, this ut is actually the evolution operator, and this x and y are coordinates within the left region. Notice that we only consider the kernel within the left region because we want to find the probability of finding the particle are located within the left region at time t. And here, notice that the phi p are the momentum eigenfunction solved using the coordinate equation in the context of a specific potential Vx. So the key idea is we make a spectral decomposition of the kernel, and we find that the decay is governed by two different things, the two different modes, exponential decay mode and power law tail. And using these expressions, we can identify the transition between these two regimes and to find when the exponential decay regimes begins and ends. So here is the technical details of the decomposition of the kernel. Here we analytical continuate the energy to the complex plane, and we found that the kernel can be written as a sum of the function f and g. But notice this function f is actually a counter integral showed in this red counter in the plot. And this function g actually is actually an integral along the inverse direction of the imaginary axis of energy E. So why is it valid? Well, notice that this arc of this counter integral and infinity actually its contribution can be ignored because it is exponentially compressed. So this counter integral f actually only has two contributions. The one along the real axis, which matches the original expression of our kernel k, and the other one along the direction of the imaginary axis of energy E. To neutralize the contribution from this one, we add this function g along the inverse direction. So as f and g, we obtain the original kernel k. And now we only need to evaluate the counter integral f and the integral g separately. So for the counter integral f, well, given a specific potential function, we can calculate the eigenfunction phi p and found the poles of these analytical functions, and which represented as these poles E0 minus IH bar over 2 gamma 0 and E1 minus IH bar over 2 gamma 1, such as this. These are poles of these analytical functions. After that, we can use the residue theorem to evaluate the counter integral. And we found that it can be expressed in the series of exponential function like this. And for the other integral g, we can use the later time expansion and found that it can be expressed as a power tail and a power law tail, such as this. Okay. Uh, Hence, we obtain the decomposition of the kernel with the summation of a power law tail, which shows as blue terms, and an exponential decay, which was showed in the red terms. And notice that the second approximation actually is the approximation for the leading order mode of the exponential decay, because we know that the lowest order of the exponential decay will take over the other mode of decay E1, E2, and E3, and something and etc. Well, so this second approximation is actually represent this, and we make some concrete calculation for three different uh, potential Vx in the appendices of our paper. So appendix A for the square barrier potential, and we find this power law gamma equals to 3 over 2. And for appendix B, we study the modified square barrier, obtain the gamma equals 2. And for the appendix C, we study the Post-Taylor potential and find the gamma of 1 over half, and find the gamma equals 1 half. And then it's our main result. So using that decomposition of the kernel, we can find the so-called dawn time, which means the onset of the leading order mode of the exponential decay, and the twilight time, which represent the ending of the exponential decay. Uh, Yes, and we find that the dawn time depends on the initial state, while the twilight time is a universal structure, which means it's independent from the initial state. Now, first we derive the low twilight times expression. Well, actually, the idea is very simple. Come back to the expression for the kernel. Uh, Using the second line approximation, we know that there are two contributions of this kernel. One exponential decay, and the other one is the power law tail. So if we take the modular square of these blue terms and red terms and compare them, we can find when does exponential decay takes over, then the power law tail and inverse. And that's how we obtain the so-called twilight time. And compare these two terms, compare the module square of these two terms, we obtain actually a very simple analytical expression for this intersection time t. And notice that the argument of this Lambert W function and the time are all real. That's why only the W0 and W minus 1 branch are considered in our twilight time picture. And the plot in the right hand side shows the plot of the W0 and W minus 1 branch. So for a specific argument, we can find that there are two intersections for uh, uh, at W0 and W minus 1. And because we know that in later time, the power law tail will take over than the exponential decay. So the real twilight time is the later one. And notice there is a negative sign before the Lambert function. So actually the real twilight time is the intersection in the W minus 1 branch. However, the other intersection can also be useful in later derivation of the dawn time, which we will discuss in details in the next slide. So for the back and for the thick barrier limit, we obtain actually very beautiful and elegant expression for the twilight time, which shows below. Well, for the for the square barrier and the modified square barrier, this twilight time approximate to 4 gamma kappa b minus a over gamma 0 h bar. And for the Cauchy-Taylor, this twilight time equals approximates to 4 gamma pi kappa over gamma 0 alpha and h bar, alpha h bar. So here the notice that here the p0 is actually the lowest mode of the resonance momentum associated with the metastable decay, metastable state. And physically, it corresponds to the Cauchy bound state, which temporarily trapped in the left region but can leak out. So actually, it is slightly complex, but here we only use the real part. And for the more technical details, you can check the appendices of our paper. The dawn time is a little more complicated because it is dependent on the initial state. So here, these blue terms psi y0 is the initial state, and the red terms are the kernel we have used. So we were using the late time expansion of the kernel, such as just like we have derived before. And in the same time, we can decompose this initial state wave function psi y0 with respect to the eigenfunction in the left region. Yeah, and we can obtain the wave function at time t, the expression for the wave function at time t, psi xt, obtain this expression. So what is the dawn time? The dawn time means the definition of dawn time is when the leading order exponential decay dominate. So actually, we can study the second terms of this expression. Yes, and we can use this inequality to find when the gamma 0 or the leading order exponential decay taken over all the other exponential decay, such as gamma 1, gamma 2, gamma 3 to gamma n. And notice that for this function we used in the inequality f2, we used another integral over coordinate x. The reason is because we want to make x and y symmetric, and well, eventually the dawn time should be independent of the coordinate, obviously. And using this inequality, we actually find the first terms of the final expression for dawn time. And for the reason why we also need another term is that for some specific situations, we find that the first terms will be negative, which means that the leading order exponential mode take over all the other exponential decay mode at the beginning. And so in that case, how to find the dawn time? Actually, that's where we can use the other intersection in the Lambert function because it's the earlier intersection. So in that case, actually, when the leading order exponential decay take over the power law tail, that time is actually the dawn time we want. So that's how we obtain the final expression of the dawn time. And here we show an qualitative time evolution of the probability PL of finding the wave function in the left region L for a given initial wave function psi 0. And we actually calculated all the analytical expression for all the time we mentioned in this plot, the dawn time, the twilight time, and even the dawn, this T prime means when the next to leading order exponential decay begins. We also calculate that, and it is possible. For the concrete technical details, you can check our paper. So there are some universal structures appears in this analysis because in some other places similar exponential regimes in the middle in the intermediate in the intermediate time also appears. For example, in the black hole randoms causing normal modes and in the cold atom tunneling experiment. So the universal pattern is very simple. In the early time, power law will dominate, and in the intermediate period, an exponential decay regime appears, and later time, the power law tail take over the exponential decay regime again. For the future direction, well, it first I want to extend the analysis to quantum field theory, and that's what I'm currently doing. And for the application, of course, obviously it can be used in electroweak phase transition in early universe. And actually, it also connects to the real. It also has some connections. For example, it's related to real-time dynamics because if we can calculate the kernel in the left region, then we can also calculate the kernel in the barrier region and in the right region, and we can use it to monitor the real-time dynamics of the wave packet. It is possible. And second connection is actually it's related to the so-called Picard-Lipschitz theory using the Lipschitz symbol and the saddle approximation to evaluate the decay rate in real time also. There are some papers using that method, but they don't give the analytical expression for the dawn time and twilight time. But I think these two methods are actually equivalent and can be proved. And that's my presentation of my master research project. Thank you very much.